Hello, and welcome to Chapter 9, Section 2. Today we are looking at a hypothesis test for a proportion when we are trying to make a decision about a population proportion. So the name of this hypothesis test is the one proportion z-test. So just like how when we made our confidence intervals, we had the full panic process, in a hypothesis test, I also have a fun acronym for you to help remember all the different parts that need to be included when we perform a hypothesis test. My acronym for this is PHANTOM. So not as fun as panic because it's not a verb, but for PHANTOM, it starts off much the same way as we would with panic. We're going to start off by stating our parameter. So what are we trying to make a decision about? Is it a population mean? Is it a population proportion? And what is the context of the problem? That all needs to get included in the parameter. Then in the hypotheses, this is the whole point of a hypothesis test. We have to state our hypotheses. So our null hypothesis and our alternative hypothesis, we would just want to state those in symbols. Next, this is something that's familiar to you, the assumptions and conditions, which is the same as what we've been doing with our confidence intervals. And then N stands for name of the test. So in section 2, in this section, we will only have one name so far, just the one proportion z-test. And again, the name changes based on the type of problem that you have. Is it a proportion? Is it a mean? And so on. Okay. Then the next thing is the T. This is something that's new to us. So the T stands for test statistic. A test statistic is just like a z-score or a t-score. So keep in mind, our goal of the hypothesis test is to eventually calculate that p-value, that probability using the normal curve. So in order to calculate a probability using the normal curve, we would need a z-score or a t-score, because if we're using the t-distribution, we would have t-scores. So that's all a test statistic is. It's just that name so that we don't have to say z-score or t-score. And so the formula for it, this is pretty much the same every time. So the z-score formula is usually the x value minus the mean divided by the standard deviation. Well, it's going to be similar because because we're dealing with samples, we have the sample statistic, so either a p-hat or an x-bar, minus the mean, and so this is the parameter, the population parameter that we're talking about now. So either the lowercase p for the true proportion or the true mean, divided by the standard error. And remember, we have two formulas for standard error. So we have the one for proportions. Just notice that this time we have p hat instead of p times 1 minus p, because now we only have the value of what we got from our sample. Or we have the sample standard deviation divided by the square root of n. So these are our formulas, and depending on whether our standard deviation is from a sample or a population, that'll determine for a mean whether it's a z or t score, much like our confidence interval chapter. The next step in our phantom process is the O stands for odds. It's really just the p-value, but I gotta make my acronym, so O for odds. And then the last step is the M stands for make a decision. This is really just your conclusion. Again, I just needed an acronym. So as you can see, just slightly more steps than our panic process here for a hypothesis test, because we have a few more calculations to do. So the best way to demonstrate this hypothesis test in the full phantom process then is with an example. And of course, what better example to use than Patrick Star? So, I don't know if you guys know, Band Geeks is my favorite episode. Patrick Star has difficulties naming instruments in this episode. It's just hilarious. So based on this episode, he can correctly name an instrument 33% of the time. And I'm like being generous here because he names mayonnaise. We assume he's naming horseradish, but he is holding an instrument of some sort. So I'm assuming at some point his brain was like, all right, this could be an instrument. So 1/3 of the time he can name an instrument correctly. So Squidward is having difficulty believing Patrick is even capable of accomplishing this much and believes his real score should really only be 20%. Is there convincing evidence that Patrick's ability to correctly name an instrument is any different than that 20% that Squidward thinks? So, in this problem, a lot of times the question will say something like, is there convincing evidence? And that's kind of how we know this should be a hypothesis test. And first of all, like, is there convincing evidence is like a yes or no answer, which when would the AP test ever be that easy? Never. So when we say, is there convincing evidence, just know that's should be a clue to you to do a hypothesis test. And so when you think hypothesis test, we need the full phantom process. So let's get started. For our parameter, we are trying to find the true proportion of times Patrick Star can name an instrument correctly. And we know this is a proportion problem because we are given percentages and not means. Next is to write our hypotheses. So when we write our hypotheses, remember we have the null hypothesis and the alternative hypothesis. And when we write our hypotheses, we need to make sure that our symbols, our numbers are always talking about a population parameter. So it's like the proportion or the mean that we're claiming, and not from a sample. So in this problem, we are given two percentages, so we need to determine which one is actually the one to use. So this 33% is just talking about this episode in general. And then the 20% is like Patrick Star's like overall abilities. So because we're talking about the overall abilities as more of a population, the 20% is the number to use in our hypotheses. And remember, our null hypothesis and our alternative hypothesis should be using the same numbers. So, and also remember in your null hypothesis, it's the one with the equal signs. So since we're dealing with proportions, we'll use P equals and then 0.20 because that's our population proportion that we are trying to determine whether this is true or not. So our alternative is going to be P, and then here we get to choose our greater than or less than or does not equal based on the question. So here we are asking, is there convincing evidence that Patrick's ability to correctly name an instrument is any different than 20%? So they haven't talked about like greater than 20%, less than 20%. It's just as long as it's different than 20%, this makes it so that anything that's different than 20% would be what we're testing for. So here we should be using the does not equal sign. All right, so here's our hypotheses. Okay, this next step, we are supposed to spell out phantom, so A is next. So for me personally, I just logically in my head, I do things a little bit out of order. I know phantom is spelled P-H-A-N-T-O-M. When I do that, my hypothesis test process, I do P-H-N-A-T-O-M because to me it makes a little bit more sense. And here's the reason why. So N stands for naming the test, right? Okay. So if we figure out our assumptions and conditions before we name the test, it's kind of weird because like really we need to know what test we are doing first before we figure out which assumptions and conditions we need to check for. So that's my logic to it. Really, as long as you include the A and the N in whatever order, we'll be fine. But to me, with my logical brain, I like to do the N first to name the test and then state my assumptions and conditions. So here we name our test one proportion Z test. So I'm telling people this is the test I'm doing. The reason why I need to name it is because as we go on through the rest of our chapters, we're going to add like 9 more names to our list. So, you know, there's that to look forward to. All right. So, and this is a Z test rather than a T test because we will be using Z scores and the normal curve. Because with our proportions, like with our confidence intervals, whenever we did a proportion problem, we only use Z star. So that's the same logic there. All right, our next step is our assumptions and conditions, and this is where it gets a little awkward because I really wanted to use a SpongeBob example, but trying to make this into a nice statistics problem is a little awkward, but we'll go with it. That way you can see some examples of like how when things don't work out, this is what you should say. So if we are looking for random independent samples, well, for us, a sample for us is considered like an episode, I guess, because we're saying like in the Band Geeks episode, he can name an instrument 33% of the time. All right, so we, again, the word assumptions, we're going to have to assume some things. We will assume that each episode where Patrick names instruments are random and independent of each other. I don't even know how many episodes where he actually needs to name instruments because I stopped watching the newer stuff because it's not as good. I said what I said. All right, then, so we stated, we checked for randomness, we checked for independence, and we did the best we could. Okay, then checking for normality, we need our large counts condition because we are dealing with proportions. So that's the n times p times 1 minus p has to be greater than 10. Well, also awkward here is because n for us in the Band Geeks episode, he only tries to name an instrument 3 times, and he gets it correct 1 time to get our proportion of 33%. So n for us is really just 3, which is not a good sample size, whether or not our proportions, like p is like a good number or not. 3 for your sample size is no bueno, but we will go with it. So when we do n times p, we get 3 times p for us. So here we are dealing with the proportion from our hypotheses. So this is the p for our population proportion, 20%. So keep that in mind. So when we multiply that, we get 0.6. This is obviously not greater than 10. And then when we do n times 1 minus p, we get 3 times 0.8. We're going to be a bigger number here, but still not bigger than 10. Okay, let's say this was the case. So if this is the case, you ever get n times p, n times 1 minus p for both of those not to work, or for either one of those to not work, we want to say something just acknowledging that, like, we know this failed. So we will say the large counts condition is not met, so our distribution may not be normal. So we've acknowledged that we might not have a normal distribution here. When we calculate our p-value, this may not be accurate. So really, we are just letting people know, like, this might not work. Whatever decision we make from this is probably not going to be accurate, but we're going to proceed anyways because we got to do this problem. But just know the end results might not be worth anything. Alright, so we've stumbled our way through our assumptions and conditions. So next up is test statistic. So our test statistic, we're trying to calculate that z-score. So our formula looks like this, and I'm slightly different than what I said earlier. So the standard error for the bottom is actually just regular p, not p hat, times 1 minus p all over n. Sorry, messed that up. You might want to go back up to change your notes on that one. Okay, but plugging things in from here, p hat is the proportion we got from our samples. So that's when we said 33% was Patrick's accuracy here. And p is the number from our hypotheses. So that's the 0.20. And so our standard error is found using that hypotheses number. So 0.20 times 1 minus 0.20 over 3 as our sample size. And from that we get a z-score of 0.5774. Okay. So moving on, next is our odds. So again, when we calculate our odds, it's based off of the normal curve. So I've labeled my mean and standard error for my normal curve here. So remember, we are trying to test for the observed sample statistic, which we got 0.33. So 0.33 falls to the right of 0.20 of mean. And remember, we're always shading away from the mean, so we're shading to the right. And then looking back at our alternative hypothesis was that does not equal 0.20. So that makes this a two-sided test because we don't care whether our sample is going to be greater than, or sorry, the true proportion is supposed to be greater than or less than the 20%. So with a two-sided test, not only do we have to find the probability that the true proportion might be greater than 0.33, but also less than. And I'm not so concerned about the actual number, the x value that goes over here, because once I find this probability to the right, I can just double it because, you know, the normal curve is symmetric. So what's on one side should also be on the left side as well. So when I double it, then that'll give me the probability of both sides. All right, so just looking for the probability on the right side, where z is greater than a z-score of 0.5774, I end up with a probability of 0.2818. So that'll just give me the probability on the right side. If I double that, so times by 2, then my p-value is going to be 0.5637-ish. All right, so that's my p-value. Remember, we were looking for that p-value, whether it's high or low. Yeah, this is definitely not a low p-value. All right, our final step is to make that decision, otherwise known as our conclusion. So in the conclusion, we basically sound the same every single time. So I've made it so that you can just fill in the blank here. So this is like the generic fill in the blank version, and then we'll fill stuff in, and I'll show you how this whole less than, greater than, reject, fail to reject works. So first, our p-value of and then you want to state your p-value. So the reason I made this into like a fill in the blank portion is because on the AP test, they're very specific about what they want you to say when you finally make your decision. So we have to include what our p-value was. Obviously, they see you calculate it, but you want to mention it. We also want to compare it to our alpha level. So remember, that was the significance level. So whether or not it was greater than or less than alpha, that told us whether we should reject our null hypothesis or fail to reject it. So that's why we want to include that here. So I'm just going to fill in my p-value of 0.5637 is, and then we need to figure out what alpha level are we using. Well, in this problem, they didn't actually tell us. So alpha level is, kind of like that confidence level. In the past, you've always been told what confidence level to use. Here, if they don't say, you get to choose whatever significance level you want, you can use it. The most common is the 1%, 5%, and 10% alpha levels, the significance levels. Again, up to you. The most common one is the 5%, so the 0.05, because that correlates or corresponds to a 95% confidence, and that's pretty good. So we want to say whether our p-value is greater than or less than this number. It is definitely greater than. So I'm going to choose greater than. So and remember we said if our p-value is not low, then we don't reject HO. So we fail to reject HO. Okay, so that means, remember, the lower probability that you have, the more evidence against HO that you have. We don't have convincing evidence because our p-value was so high. So there is not convincing evidence that blah, 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 blah. Okay, so one thing I want you to notice here is every time we pick the second option out of our fill in the blank stuff, it's always the second options that go together. So greater than always goes with fail to reject, always goes with is not convincing evidence. So if you choose less than, meaning you had a low p-value, then you're going to reject, and there is convincing evidence. So that's how we always choose it. I try to make it as easy for you to remember as possible. Okay, and this last part, fill in the blank, we are trying to figure out if we have convincing evidence that, and we just want to restate the question. So in this problem, we were saying, is there convincing evidence that Patrick's ability to correctly name an instrument is any different than 20%? So we don't have evidence of this. So we are saying Patrick's ability to name an instrument correctly is any different than 20%. So we are saying this is not true. All right, so that concludes our full hypothesis test, the whole phantom process. I know it's long, I know it's tedious, but that's everything that needs to be included in order for you to get full credit on the AP exam. All right, so now that we can correctly do a full hypothesis test, there's one more thing I want to talk about, which is the power of a hypothesis test. So power, this is good, it's a good thing, you want power. Power is when you reject the null hypothesis HO when HA, your alternative hypothesis, is true. In other words, you are rejecting HO correctly. So this is a great thing. So when you're not making an error, you have power. So before we get into calculating the actual numerical values of power, I want to talk about the probability of making a type 1 error first, because it has to do with all that. So probability of making a type 1 error, remember type 1 error is when you reject your null hypothesis when you shouldn't. So we reject the null hypothesis when our p-value is less than alpha. So visually, if we had the normal curve, alpha could be either on the right side or the left side, but whatever area that is, if our p-value is also in that area, then that means we would reject. So if we reject when we shouldn't, then the probability of us making that error of rejecting would be anywhere within the area that alpha covers. So if alpha was 0.05 for our significance level, then the probability of making a type 1 error would be 0.05, and so on. So then let's talk about a probability of type 2 error. All right, so probability of type 2 error is actually a little bit more complicated, because remember, type 2 error is when you fail to reject HO when you actually should reject HO. So if we're saying we should reject HO, that means HO wasn't actually true. So in this picture, it's more complicated. I stole it from the textbook because they did a really good job of making it beautiful. Okay, so in this first picture, I don't know what problem this is for. I wanted their picture. They're saying their mean is like 0.08 for something. And this was their, so this green line right here is basically what alpha is. So that's anywhere in there is where we would reject HO. And so that's the probability of type 1 error right there. So if we're saying that HO is not true, we should have rejected it. That means this mean then can't be true. If this mean can't be true, we're going to draw a different picture here, and that's why there's this other normal curve down at the bottom where we have a different mean. So again, I don't know if this mean is true or not, but we're going to use it as an alternative to what the original HO value was. So if we're using this as an alternative HO value, our sample, we still would have gotten the same number, whatever it was, somewhere in this alpha level, hopefully. But whatever that number was, then our entire curve, our normal curve, would shift a little bit to accommodate that. But alpha would still remain in the same spot because just because it's a different normal curve, it doesn't mean that you would reject anything differently. So the same x value where you would start rejecting would remain the same. So this x value here, that's why it's like straight vertically down. Everything that's shaded here, this is where we would reject HO because it's kind of like the alpha from before. This is where the shaded area is where you would reject HO. So rejecting HO is over here. That means this unshaded portion in this normal curve is where we would fail to reject HO when we really should have. So this probability here is the probability of type 2 error, where you fail to reject when you should. This error right here is not something that you're ever asked to calculate on the AP test, which is nice because the process is a little bit complicated. And in the textbook, they did do it just, to show you that it can be done, and it can be done. You have all the skills to do it. It's just a little bit more tedious of a process, so we aren't required to teach it. Cool. But you do need to know that a lot of times the symbols used for the probability of type 2 error, we just call it beta. So, it's kind of like the Greek alphabet. We go from alpha, beta, and so on. So beta is the probability of type 2 error. So earlier we were saying this whole shaded area over here, this is when you would reject HO when your HO should have been rejected. Because remember, this new normal curve is where our HO is now hopefully true. So we should be rejecting HO because originally HO was this number over here. We rejected it, made a new number for our alternative. So this would really be our HA here. And so if HA is true and we are rejecting HO, that means we have done everything correctly. This area right here is power. So because this is on the other side of where our type 2 error was, we could find that probability by doing 1 minus the probability of the type 2 error. So in other words, 1 minus beta. So on the AP test, a lot of times they'll give you what the type 2 error was, or they'll give you power, what the power is, and they'll ask you to find the other. So that's more of an example of what you might see rather than calculating everything yourself. And the last thing that I want to say about power is, how do we increase our power? Obviously, we want to be more powerful. So to increase power, there's 3 simple ways. If you increase your sample size, this will increase power because that will decrease your variability. So your standard error decreases, so your entire normal curve kind of squishes together because it's more consistent, less spread. And so this whole area that's shaded for our power also increases. Then another way is if you could increase alpha, because if you increase alpha, so looking back at our picture here, that means this shaded area, the original alpha, would also increase. So this shaded area would shift a little bit. Our green line over here would now be like over here because you're increasing the level of alpha. And so if you're increasing that green line over here, or sorry, moving it to the left over here, then it would also drop down and you would end up with more shaded area on our power as well. Okay, and lastly, we can increase the distance between the value of HO and HA. So this one's a little awkward because if you remember, this first normal curve was where we were talking about assuming this number here in the middle was HO. And so when we move the HA number, so whatever number we're assuming to be our alternative, the further away it gets from HO, the more that this normal curve, the new one, would shift either to the right or to the left, whichever direction. But the further away it is, the more that shaded area would continue to get shaded because this green line stays the same. So shifting this entire area over to the right, if you can imagine, this normal curve will now become more shaded because we're shading from the green line onwards. So those are the different ways to increase power. And that concludes our section 2 and our hypothesis testing. Thanks for watching. Don't forget to like and subscribe. Bye.